We've been doing a lot of work looking at unbalanced forces in one dimension. So for instance, the lift pushes up with 2000 newtons and weight pulls you down with 800 newtons, and applying Newton's second law to that situation. And in that case we usually call that the unbalanced force. But another phrase that means the same thing basically is resultant force. But that's a phrase that we usually associate with vectors at right angles, or at any angle for that matter, rather than one dimension. But just to clarify, unbalanced and resultant force both mean the same thing. It's just usually we talk about unbalanced force when we're dealing in one dimension, two-dimensional or even three-dimensional resultant force. So the resultant force, just like the unbalanced force, means what single force could do the same job as all the forces that are present. And what we've seen already is that you've done resultant displacements, resultant velocities, where you add up the individual vectors to get the resultant vector, and it's just the exact same idea. So here's a worked example here taken from your booklet, and we've got a packing case, we've got forces at right angles, so we know that in there is a right angle. Now notice though that these forces are not nose to tail, so this is a situation diagram. This is showing you the two forces acting at the same time. But if we are going to find the resultant force, then we're going to have to draw the diagram again to get properly to get the resultant force. Now there are two ways of approaching this question. You can either do it by scale drawing, or you can do it using Pythagoras, because it's right angles. And I know in my experience most students prefer the Pythagoras, the calculations. What I would say though is if it's not right angles, then I would suggest that you probably are better in that case using scale drawings. So what we've got to do, the correct way, remember, is nose to tail. It's obvious with displacements. If you walked 100 metres and then walked 50, you would start the 50 from where you finished 100. But the same applies to forces and to velocities as well, that when you're adding to find the resultant, you have to add nose to tail. And we know that there is a right angle. And this is just a sketch, so we're not doing to scale or anything like that. And our resultant force then is that single vector which can do the same job as the two. And then we can use our Pythagoras, so a squared equals b squared plus c squared. We'll label that a so it's clear. So it's 100 squared plus 50 squared, 10,000 plus 2,500. A is a square root is 112 newtons. And then we're going to label this angle in here x. Now I would always suggest you take the angle at the start rather than at the end. So in this case I happened to draw the 100 Newton one first. You could have drawn the 50 first, but we'll see how we express that in a wee second. So tan x is opposite over adjacent, which here is 50 over 100, it's 0.5, so x is tan to minus 1 of 0.5. Remember, don't just run everything in one line. Equals 0.5 equals 27 degrees. And then to express this force, then we don't have, there's no point in this diagram as it said the top of the page is north. You might be tempted to assume that, but it's not mentioned that at all. So all we can do in this case is express it relative to the forces involved. So we'd write our final answer as the resultant force so 112 newtons at 27 degrees to the 100 Newton force, because that's where x is beside.